because I believe that kernel functions are quite interesting, and although they're been used a lot more in the past with models like support vector machines, the kernel functions, I think, bring some intuition to a model like a transformer. And so let me talk just first a little bit, a few slides about kernel, and then I will revisit the transformer with but through the eyes, through the lens of a kernel function. And so kernel function it acts as a similarity metric between data points. I have two data points, and I would like to know how similar they are. And I can do just a dot product. It's a type of kernel function. Or in most cases, what will I do is I will do, or at least do the equivalent of projecting my data into another space. And that's what this projection function will. You can call it a projection function. And that projection function will allow me, and hopefully by projecting my data in that other space, then the similarity between data points will be more obvious. That's my hope. And I was doing it a little bit earlier when I was just projecting linearly with W, but the general kernel can be projection a lot more complex. And so notation wise, sometimes the inner product of two will just be denoted with this these kind of bracket. And the X is my data point, but the projection can be in any space. So usually the space for the input will be more the real world, the real space, but although it's not necessary. But the other one could be another space, and I will give you some examples soon. But before I give you the more complex example, I just want to go, and you may have seen that, is like this data is hard to separate with a linear, with a line. But if I project it, and this is just a square of the data point, so whatever square of it is, that's what I project here. That's what the z is just the square of x squared plus y squared will be just the z. Then it becomes very obvious how to separate. And if you remember, a neuron is a linear classifier. So remember that although we're going to very complex thing, it is at the end of the day a linear classifier. Although you can have after that you add the nonlinearity, but the basic of it is like each neuron is doing a local classification. So want to map our data to a linear separable space. That's a little bit what we doing. And instead of doing that classification, that linear separable is in the X space, you're going to do in this other space, which hopefully in that other space, it will become obvious what is close to each other and what is not. But if this one becomes very, very complex and very high dimensional, then it can become expensive. And that's where we come to what's called the kernel trick. The kernel trick is really interesting. Is the idea that I would like to compare these two in a very, very high dimensional space, but doing that will be computationally very challenging, or maybe not even feasible. Instead of that, I'm going to directly compute how similar two samples are. And the more classic one is RBF that you may have seen before. So this is an example of the radial basis function. And in this case, what is the projection? What is that projection function? Although the similarity, like how similar two data points are, is a relatively simple function. The projection is in fact it's infinite dimensional. And so that's really interesting that the kernel is a similarity function. And the kernel trick is that although if I was to do the full projection, it would be very complex to do, or impossible in the case of the RBF. but computing the similarity in that space can be analytically written directly, and that's really powerful. And so another example, and one of this, only a hyperparameter of this, although you see an extension with more hyperparameter, but a classic hyperparameter is it, which is really low sigma, the model becomes nearest neighbor, because at that point, what it means is you're only going to take the influence of very local. And if you make it very large, you're also going to be influenced by the data point that are a little bit further. That's a little bit what the intuition you could get from that. There's been over the years many different kernels, and I invite you to like take a moment to look. There's some that are specifically for histogram, for string. There was pyramid matching for looking at hierarchical data. There's a very large family of kernels that have been, a lot of them in late 90s to early 2000. There was a lot of work around them when support vector machines were really popular. And so when these, what they give you is new tool to do local similarity measure. And if you remember when we studied CCA, canonical correlation analysis, where we were looking at like embedding kind of two modalities or 2 points and looking at the correlation, but the correlation over many different canonical axes, if you want, bases. Canonical in our case were perpendicular. And in this case, we did it in a linear case, and we showed extension of that did it in a multimodal sense and also in a nonlinear sense. And that was what the kernel, that is an example of a kernel. So a kernel can be computable. You can, the way of computing that kernel similarity could be by projecting each data point and then taking the dot product. That can be the way the kernel end up being computing. But as you see in other work with the IBF, it could be that at the end of the day, I will not take the time to project, and I will find a way analytically to get the similarity directly. Great. The reason I go all the way there is that now I can revisit the transformer, the one we love so much, the transformer, and that key place. I mean, this is one of the key thing, I mean, of a transformer. They have I have this query, and each of the key, which of the key is the most relevant to my query. But if I want to know which one is the most relevant, I need to be able to know which one is similar, relevant, or similar. And so how can I recompute this in a kernel sense? How can I present this as a kernel? This function here is a kernel. This is, you can formulate this as a kernel. The attention, in fact, the softmax also, the top part here is a kernel, is a similarity. It's a simple one, it's a dot product, but it's still, it is a kernel. And the softmax, what it does is just a summation that you do over these kernel between the query and all possible k that you had. So that's what the softmax is doing. So this, what's really nice is this formulation that we know, it could be seen as a kernel function. And then you can start thinking, if I have multimodal data, or even unimodal maybe, but even more if I have multimodal, where my query may be quite different from my kernel, what is the perfect kernel? And then I can go and revisit. You can go and revisit some of these kernel. This is like the conventional transformer that looks at it as an exponential function, and you just have a linear projection for each of them and then the dot product. But then you can start and revisit some other, this is for the task of neural machine translation, which a lot of the time is evaluated with metrics. None of the metrics are perfect. So one of them is BLEU, B-L-E-U. And it's interesting. And I know the difference is not big, but if you work in machine translation, you will say, this is a decent improvement. It's not like the world changing, but it's interesting that just changing this little thing like a better similarity function or a different similarity function can have an impact and improvement. Any improvement in this case can be good in machine translation. So, and then what you can also ask yourself is you have also position embedding. So I have position embedding, and if you remember, right now in a typical transformer, how did I integrate the position of my query and the position of my key? I was sometimes just summing them, but there may be other ways to do this. And one example is to say, hey, I have my position embedding for my query. I have my position embedding for my key. Let's use a kernel, a similarity function to infer the improvement. And that's really interesting because here, what I did is I just changed. The only thing I changed is my kernel of the position embedding. And I get a very decent improvement over a classic transformer. While XLNet does slightly different, it does multiply it, but still doing a kernel, a different kernel for the, you don't want sometimes maybe the same kernel for how I do the position embedding and how do I do the embedding of the embedding of the key and the query. So the key and the query values, but I also want to be at the same time to do a different kernel for the position embedding. So I wanted to bring this because that gives you the idea of local embedding. That was a transformer, and that was a proposed one. This is another new-ish. I didn't put the icon, but it was a new-ish paper from EMNLP 2019 on this. And here in this case, they had a different one for the value and for the position embedding, the value embeddings and position embedding. So, and now you can ask yourself this concept of local similarity or local fusion. Can I use it like in a multimodal as a fusion mechanism? You remember in late fusion, I have each modality and I just want to do a late fusion. And you can also use a kernel for that late fusion. That's really interesting. And that's that will be called multiple kernel learning. And there, what you will do is you say each modality, what is the right kernel? What is the right way to compare two modality or within one modality? What is the right way within the modality? And maybe you can extend this idea. That's not what is currently shown in this figure, but you can extend this idea that is also kernels between modalities. And so multi-kernel learning will be like, I have multiple ways to look at similarity, and I will use either I will pre-select or I will use all of them. And so you can use this idea by saying, hey, similarity there within one modality. I could have many different ways one modalities can be seen from a similar perspective. So I can see two sentences, and are they similar? I could ask myself, are they similar grammatically? Are they similar because of the sentiment? Are they similar semantically? So there's different ways. Even within the modality, things can be similar. And then there's also ways between modalities where like, hey, these two are similar, not just because it's grammar, but it's also the grammar and the facial expression as well. So this is the wrap up on the fusion side of the multimodal. The last part of this lecture today is going to be about co-learning. Co-learning is this fifth multimodal challenge, the underdog of multimodal. And I think very interesting cases can be done there. And there's really interesting research currently and future research to be done in this area. The idea of multimodal or co-learning, the main idea is to transfer knowledge between modalities. That's the key aspect. It's like I have a task within a modality and I want to transfer some knowledge from the modality, the second modality, to help me better predict in my original task. And it could be through sharing knowledge about the representation or sharing knowledge on how they do prediction on that task. That can be done at different level, but that's the idea of bringing extra knowledge, not being eventually at test time. It may not even be done, maybe not even be used that modality at test time. It can be only just modality one. And to do that transfer knowledge, you will need some pairing. You need to have paired. And in the original multimodal machine learning survey, we called them parallel and non-parallel. Over the years, I changed it, and I can go change at the archive, but at least internally, we call it strongly paired and weakly paired. I think no pairing at all will be, if there's really no pairing, data that are completely different, unrelated, that will not, will make the problem either impossible or very hard. But there is the idea of weakly. Strongly paired will be for every for every data point in one modality, I have an equivalent in the other modality. And so for every word, there's an image, and I have a lot of these paired data. Weakly paired will be, I have a bunch of images, and I know that they're kind of related to this bunch of words. I know that's related at some level, but it may not be clear when. And so that's a weak pairing into that. So let me give you the simpler of the two with paired or strongly paired data. One example, there are many of them. This is just one example. This is a paper on word embedding from visual co-occurrence, where the goal was to learn better word representation. And word representations, sometimes, unfortunately, because they're learned based on the context of the other words, there's some aspect of their physical representation that is not correctly identified. There's some attribute like the roughness of something, the softness of something, like of an object, may not be in that embedding. Is that knowledge is a lot easier if you touch it, or if you see it. Like if you see or touch the object, then you gain some knowledge about an object that is different from, this is a laser pointer. I can see where I use laser pointer in every sentences on Wikipedia or on the internet, but that may or may not tell me how soft a laser pointer is, how long it is. And so can I bring that knowledge from the attributes, from the visual attributes, bring that knowledge in my embedding? That's the key idea. That's one way, an example of like, and in this case, I will have strong pairing. So for many words, I will have attributes of it. So I have these words, and for each of these words, I had manually, some people annotate each of them with attributes. And then I can go and learn during learning, during training, I can go ahead and learn an embedding, a new embedding and visual of the text. And the specific of this was done with a log bilinear model. Do you remember the bilinear model where you simply like the product of these two vectors, that gives you a nice complex matrix that gives you all possible interaction. So you have your word embedding, your attributes, and you got the bilinear model. You can do a log version of that. Since this video is learned from multiple type of occurrence, we have the hypothesis is that the new embedding, once you get that log linear, you can just project it into maybe a vector after that. So the nice thing is one axis is the attribute, the other one is my embedding, word embedding learned without the visual co-occurrences, and then I get that bilinear, and then I can go and reproject it. And then when you do that, you learn, you can learn an embedding that will hopefully better represent the attributes, which is not too surprising. I took an embedding and I kind of force it to cluster it, and then it gives you the other. But it's still nice to see it and show this example. I'm gonna give you another example. This one I talked in the first lecture, but one of the first lecture. But now hopefully it will make. Now that we've gone through all this, revisiting this example is sometimes great. Is that you have you want a better embedding of language, of spoken language, like how people are speaking, and when they're speaking, they're not just using maybe slightly different words and writing, but they also, when they're speaking, there's a lot of emotion, and you in the voice, or there may be different aspects that also express facial expression. And spoken language, you may have less data, and let's say you have limited data to get your embedding, but you have audio and visual that could help kind of gear you during training. And so what you can do is learn an encoder decoder, and the goal of the encoder is to take my language and encode it in a representation. This is the representation I want. That representation will allow me to do tasks like maybe like sentiment analysis or something based on spoken language. But I want to do it in such a way that I'm still able to predict the visual, the facial expression that happened, that co-occur with this. One thing that was important in that early work, the newish work of 2019, was that it was important not only to do the encoder decoder, but to do the cyclic loss. The cyclic loss was important because if you just do the encoder and the decoder, this representation will be learned in such a way that it's able to generate this. But we don't want this representation to be just useful at generating this. We want this representation to also be good at regenerating the original one, and that's why the cyclic loss is important. And then you can use that to do something like sentiment analysis. What's really interesting with this model is that it ended up outperforming many of the other models that also use multimodal information at the test time. That was very impressive from it. I think it is possible primarily because sentiment has been originally defined, sentiment analysis, as a language-based task. And we know that language is a very strong component of it. Multimodal adds to it. It has been shown in many papers, but definitely language is a strong modality. If all three modalities were the same, this kind of cyclic may not have been as strong of it, or at least not as strong as the multimodal, but it was quite interesting. And in this case, it performed because this one only has the verbal, the language at the test time. I want to give an example when we have weak pairing, where you don't have always this nice link between the modalities. An example is all of those YouTube videos that you're watching or someone is watching. They watch these videos, and maybe one type of video could be instructional videos. These are great because they have a structure in it that make it easier. a typical, but when I talk, right now it's on me talking, but when we watch the news, they're showing images to enhance, to add to this story, or they show videos that accompany the news. These may not always be aligned in it, and even now when I'm talking, my gestures may not be correct, completely aligned. So there's this misalignment. It's a weak, it's not completely in the spectrum of weak to strong to weak. It's not like the weakest of the pairing, but it's definitely not I have exact pairing. It's maybe somewhere in the middle, because I have a misalignment, but because it's temporal video, it's very unlikely that the week is like 2 hours before or 2 hours after. It's probably within a few minutes that this sentence linked to the image. And so instructional videos are also good in that direction, is that there's even more, because I'm either giving a recipe, let's say cooking, or because I'm showing how to fix something, then the likelihood of me referring to some video or image from a long time ago are very small. But there's still a misalignment. And so how do I handle this misalignment? In this paper, this is one way, is to do what's called multi-instance learning. And you also do something, but to handle the misalignment is on one of the sides. It doesn't allow you to do misalignment on both sides. But to do the misalignment on one side, it says, hey, for each short clip, I'm going to look at all of the language, recent utterances, and what will I do is I will take it as a bag of utterances, and I will have the hypothesis that at least one of these is relevant, is a positive example, is relevant to this video. So the concept of multi-instance learning allows me, when formulated this way, is to be able to do, so given this video, I say, hey, which one match these, which of these match my video? And that could be, if I was just doing multi-instance learning, that could be my task. I say, hey, I show you a video clip and I ask you which of them, which one is a positive sample. So it's a nice thing. It's a multi-instance learning is the concept that you have a bag. You don't have a positive. I don't know which one is the right one. And I could go and manually annotate it, but it will be too time consuming. So instead of that, I'm going to say, hey, in one of them, I have like plus or minus 3 seconds. One of these utterances, or plus or minus, I don't know, 10, 15 seconds. One of them is going to be most likely. And there's still a little caveat. I mean, it is still possible. I will not, but hopefully in most cases I'm true. And the multi-instance learning allow you to handle that it's not exact. Now, to handle the fact that it's maybe not always perfect, and also because I would like to do it in an unsupervised way, or what is often called now these days self-supervised way, is that I'd like to take all of these instruction videos and learn to represent these instructions and insert in multiple instruction in a semi-supervised, in a self-supervised way, without manually annotating, oh, this is an instruction, this is another instruction. I'd like to find ways to embed or represent these multiple. And one way, and we've seen a little bit of that already, but I want to emphasize again the concept of contrastive learning. Contrastive learning is extremely popular these days in self-supervised learning. And I think this is, it has a flavor of when I didn't discuss in SVM that part, but in SVM, you have in the loss something that looks a little bit like this, where you want to be close to the positive bias, while at the same time far as possible to negative. It has a flavor of that. Contrastive learning is that, and here's one formulation of contrastive learning, where you want to be, you have all those positive, this mixes the instance learning and the contrastive learning, but you have some bag of positive, and you want your representation of the you want your representation of the video to be as close as possible, as similar as possible in the for the positive cases, but in general should be, I also have the negative cases, and so I would like them to be, I would like to contrast them, these, and the contrastive could be implemented. This is one of the laws for that, but in a sense, I want to be close to the things that are the same, and as far as possible from the thing that are the negative example. And here the negative example could be any sentence I spoke 2 minutes ago, which is very unlikely to go there. And so what's nice with this kind of self-supervised is that it does allow you to see, and this is just an analysis of that, to see from, this is the multi-instance learning and the self-supervised together, that shows that it selects automatically the correct, out of the positive, you see which one is the most relevant. Although you can see that others are also selected. So it could be even stronger. I think this, this contrast could be even stronger. So this is an example of co-learning that I want to talk about. And that one in the paper, if you go in the paper, you can see that they use that and they perform better on their task for the instruction videos. But the main goal was to get better visual representation. So I use language as a way to improve my visual representation. And in the paper, they show that they can then go back and just perform much better, or perform better in the task of vision only as well. That's where the co-learning comes in as well. And I want to bring, and that's probably where I will stop for today, is two more examples related to co-learning. And one is called few-shot learning. Is the idea of learning with very few examples. So I want to predict a new object. I only recently showed you, this is Bartam. This is a Bartam, and you've never heard that word. And I may be only showing you one or two examples. And then later on, you need to text. You need to be able to recognize that object. But then I could say, Bartam is something you hold in your hands. Bartam is something you can point with. Bartam is something, there's maybe something you can get from language that will help you to, and then you can look at what are the other objects that have similar representation on the language side, and that may help me to I only showed you one image or very few image or no image. There's something called zero-shot learning. I show you no images of this, but I use another modality. It's a little bit funny because zero-shot learning, I still gonna get you some supervision, some information, but I'm not going to give you direct supervision. I only use another modality to help you do that task. And so one example that also takes together some of the reinforcement learning you learned last week is that I can imagine in the few-shot learning where I want to be able to learn very quickly a new word. And so it's not only one or two samples, but I want to give you, like I say, I give you, pick up the table. You never heard what a table is. I don't know what a table, but I learned how to pick up other object. And I learned how to pick up a DAX. I learned how to pick up a BLIC. And you learn that maybe in a reinforcement learning way, where I go ahead, explore, and then I'm like, hey, what is this object? And it's and then you get some local reward or supervision from saying this is DAX. And then you go and you discover and explore. And then at test time or instruction phase, you're asked a task, and you're given reward if you succeed at that task. That like a very typical reinforcement learning case. But the thing that I like of this paper, what was interesting, is the idea that for this to work, in this case, this is a typical more reinforcement learning. But if I want to be able to work on a brand new thing that is never seen before, very few, I don't have the time to rediscover and re-explore. And the typical reinforcement learning that needs a lot maybe of these iterations, I don't have time. And so the interesting idea here was to do dual coding, where you have two types of memory. You have a fast memory that very quickly adapt, and you have a slow memory that maybe adapt. So the slow memory is done originally, but I'm ready, and many of the concept I learned was this way. But at test time or like a new, I will get some information, and then I can go and very quickly adjust that. I don't go into detail on how you do this. This is one of the paper you have to read, or you can read this. And so whoever reads it can go into detail. But it's really nice to see how this, let me go directly to this one. So it can change the mapping, and so lifting, putting all of it on new object that it had never seen. That's the example here. And so that allows you to change the relationship and also change a new object you've not seen. The last example is about weakly supervised. This is an old field. I told you there's weak pairing for co-learning. And so that is weak pairing for co-learning is a type of learning which is under the umbrella of weakly supervised. I wanted to just give another example. This one is not directly a co-learning, but it's an example of weakly supervised, where a supervised, the task may be to the task which is called phrase grounding or phrase location. This is the idea that you have a long caption and an image, and I would like to have every non-phrase or most non-phrases connected to a specific object. And so I can do that by manually annotating in the R data set. I just remember the 30K one as an example of this. But maybe I would like to only give you weak supervision, where I give you this and I tell you there are some objects that will also connect with some of these phrases, but I don't tell you which one. And so you can see it's a little bit similar to the co-learning case a little bit that I showed you when I was doing it with the instruction video. Some instances here will be connected, but here in this case, it's weak on both sides. I don't tell you which object, there are just a bunch of objects and which non-phrase are related to each other. And so one thing in that specific paper, this is one way to do it, is to leverage more. So that's the idea of weak supervision, is to, the general idea is to leverage those captions to be able to solve this. The interesting part of this is the specific one in that paper that was interesting, is to go and allow the same object to have more than one representation, and try to go and so if I just go with the typical high level like RCNN features, these have been trained for detecting man, object, and so they're very coarse level. what I would like my use of these caption to be able to learn fine-grained visual representation. My goal is to improve my visual representation by taking advantages of these caption, and to make them so that this one, it's a man, yes, but it's a man plus, if I add to it my language, it's an older man. So its visual representation of an older man will be different than a man with a red accordion. And so the idea is to shift the caption, enhance the visual representation of men by shifting it based on caption. And how do you do it? In an unsupervised way or self-supervised way? Contrastive learning, definitely. And so you will do a contrastive learning. This is the loss of the contrastive learning. And the idea is that I have some sample that are positive, and then it's over all possible sample. So that's a contrastive. And this includes both the positive and the negative one. And here you want to do it over the one that are the most similar. And the paper had a way to do that through looking at some attributes on this. So I don't go into detail on how they do that last part because of time reason. But I invite you, the main idea was the idea of the contrastive learning and the idea of getting a better representation by looking at this alignment between the alignment between the caption and the object. So, and that improves, as you will expect, the performance of this. So I thank you very much for your attention. At the end of this presentation, the slides, you will find the pointers to the papers I mentioned today if you want more details on these. Okay, thank you very much.